very much for the chance to speak here. And actually, Igor's talk is very good preparation for some of the models I'll talk about. The main difference would be, well, two main differences. One, there's an SU2 gauge field, and two, there's a finite chemical potential. But let me begin by not putting at least the chemical potential in, and just talk about insulating spin liquids on the square lattice. So we heard a lot about this yesterday. So one approach to the insulating spin liquids is to take spins on the square lattice and use a bosonic parton representation. And this parton representation leads to a U1, emergent U1 gauge theory. And so when you look at the low energy limit of this parton construction and subsequent mean field theory, you get this particular field theory, which is just two complex scalars coupled to a U1 gauge field. But most importantly, there are also monopoles allowed in this gauge theories. And these monopoles come with highly non-trivial phase factors, which today we would call some sort of 't Lipschutz-Mattis anomaly. And because the U1 gauge theory is always confining in 2+1 dimensions, you end up getting these two phases that are now seen in numerous numerical studies. The Neel state, of course, which is, you can think of as a Higgs phase where B condenses, and the confining phase with Polakov-style confinement leads to valence bond solid order because of these anomalies. And then there's the possibility, however, of some kind of CFT or critical spin liquid in the phase transition between them, which we heard a lot about yesterday. Now, there's another way to approach this same set of phases. It took a while to realize this, which is you instead use a fermionic representation for the spins. And if you use a fermionic representation, as was done by Affleck and Marston long ago, you get a dispersion spectrum of precisely the type that Igor just talked about. You get massless direct fermions, but these are not electrons, they're spin-ons. Meaning this representation actually has an emergent, in fact, has a SU2 gauge invariance. And the low energy theory is exactly the theory that Igor mentioned. There's 8 Majorana-Weyl fermions or whatever, but there's also an SU2 gauge field. And that's, so it's really quantum chromodynamics. Okay. So now you can ask, is this theory a conformal theory? Well, now we know it isn't quite, but a question you can ask, what are its confining phases? So if you do the kind of analysis that Igor mentioned, but you mod out the SU2 gauge group, then from 08 there's SO5 left over, and those SO5 order, the 5 component order parameters are precisely the same Neel and Wess-Zumino and valence bond solid order parameters, 3 components here and 2 components here. So this suggests that, in fact, this theory here is essentially the same as this theory here, and that's what's been formalized in lots of very beautiful work. There's sort of a triality, if you wish. There's the bosonic U1 gauge theory with monopoles. There's the SU2 gauge theory with Dirac fermions, massless Dirac fermions. And then you also have the representation that was used in the fuzzy sphere work, where you write everything in terms of the SO5 gauge invariant order parameter. And then all these Lipschutz-Mattis anomalies are realized by a k equals 1 Wess-Zumino-Witten term. Okay. All right. So that's really a very quick review of things we've talked about a lot yesterday. So now I want to add other phases here. So let's first stay at half filling. Now, a model that's been studied a lot at half filling is the square lattice J1, J2 model, first and second neighbor exchange interactions. And that does find both Neel and VBS order of precisely the type that was predicted. But it also finds a particular spin liquid. So this is a Z2 spin liquid, meaning it has certain topological order at some level that's identical to the topological order of the toric code or a Z2 gauge theory. But in this case, it turns out it also has gapless excitations. So this kind of spin liquid, I would say, was first found in this numerical work of the group from Trieste. And so we asked the question in this paper a few years ago, can this spin liquid fit into this SU2 gauge theory I just talked about? And in fact, we found that it fit very neatly into precisely this SU2 gauge theories. And the way you can get this Z2 spin liquid is by adding two adjoint Higgs fields. So there's a way to just go from the lattice antiferromagnet and do all kinds of decouplings and mean field analysis inspired by the numerical work and get exactly this low energy field theory. That's what this lengthy paper is all about. But from this theory, now you see that what another possibility for the fate of this SU2 gauge theory, that this Higgs fields condenses, and there's a Higgs phase in which there's a residual Z2 gauge invariance left over. It also has massless Dirac spin-ons. So that all looks great. The only problem is there are also these Yukawa couplings. And really that's what our paper is all about, analyzing the effect of the Yukawa couplings. They're very ugly in the sense they're required by the symmetries of the problem, but they're ugly because they break Lorentz invariance, SO5 invariance, and everything we love about CFTs are just broken. So one scenario, which is just a proposal here, that perhaps this Yukawa coupling, there is some conformal fixed point here, as Anders mentioned. And at that, so for this scenario to work, this Yukawa coupling would have to scale to 0 at this point. We don't know if that happens, but yes.
Is there a U1 spin liquid phase where you condense only one of the Higgs?
Yes, that turns out to be phi1 cross phi2. That's also discussed, but okay, I don't want to.
How do they transform on the Lorentz? How do they transform on the Lorentz?
This is, yeah, well, they have Lorentz vectors, and there's also other symmetries that are broken. It's complicated. Yeah, there's a gamma tau there that breaks the Lorentz symmetry. But I don't really, okay, I just mentioned this because to connect with some of the discussion yesterday.
No, it's just, I thought if they were spin 2, then we would know that they were irrelevant automatically.
Well, we don't really know. You have to go to this fixed point with the, so the idea is that if this is irrelevant, you have an SU2 gauge field with both massless fermions and massless Higgs fields. So there's some highly non-trivial CFT there, because your more gapless matter is more likely to be stable.
No, I just want to make a very trivial point. If it's a spin 2 field, we know by unitarity bound it's going to be irrelevant.
What is a spin 2 field?
The one which breaks Lorentz. You said the Yukawa couplings break Lorentz, but you didn't say which representation of the Lorentz it is. If it's spin 1, then there is a potential issue. If it's spin 2, then there is no issue. If it's spin 2 higher.
Okay, it's spin 1. I mean, it's a vector. All right. Okay, I didn't know that general thing. Yes.
On the Lorentz, isn't phi a scalar?
Phi is a scalar, yeah, but the lambda itself, lambda breaks Lorentz invariant, the Yukawa. Phi is a scalar. Yeah. So if this coupling is not present, this is a completely, it's a potential CFT, which is potentially the bicritical point that Anders mentioned yesterday. That's all I want to say here. And I agree with Anders that there's a sign problem. This is a very complicated Z2 spin liquid. It's not something you can just get with a sign problem-free representation. Anyway. Okay, let me get to something else, which is connect to the main part of my talk. Let's put in charge fluctuations. So we start with this insulator. Imagine we have a Hubbard model when we reduce the value of U, and we're going to stay exactly at half filling. And perhaps there's some other interactions that I won't specify. I can ask, could there be any other phases associated with charge fluctuations which are close to this Neel VBS transition? And actually, models like this have been studied by Fokker. I don't see Fokker today, but anyway. Okay, so let's go back to the lattice. And so this is the mean field ansatz of Laplacian Marsden, the pi flux phase. And here, I show it in two forms. This is the form that makes the spin global flavor symmetry, SU2 spin rotation invariant explicit. With EIJ, just a pi flux thing. But you can also write it in a way that makes the SU2 gauge invariance explicit, and so a Uij is a SU2 gauge field, and that's possible as long as you have this kind of bipartite structure, and the hopping is not purely imaginary. Okay, and the most important property of the symmetry is that for these spin-ons, these fractionalized particles, Tx and Ty don't commute. Now I want to put in charge fluctuation, so I will need an electron operator. Now the only way I can get an electron operator from these spin-ons is by having a boson, B, such that the electron, B and psi composite, has the same quantum numbers of an electron. So these are some charge fluctuation of charge E, and so B fused with psi gives you an electron. Now once you know the symmetry transformations of this, then the symmetry transformations of B are completely fixed, because an electron cannot have some emergent non-trivial symmetries. It has to transform, exactly like an electron. But B can have some projective factors, and in fact, this means immediately that this key relation is absolutely required also for B, because only then will the product of B and psi, will the translations commute as they have to commute for an electron. So that's all you really need to know, and you can write down some generic action for B. It also has to have imaginary hopping with a pi flux. There's a mass term, and now you can ask with some, you can also write down higher order terms. Here's the fourth order terms. And then you can relate physical autoparameters like the site density, the bond current, the pairing, to some gauge invariant bilinears of B from all the symmetries that you know. Anyway, if you just do a very simple mean field theory of this, sorry, I think this is the wrong order. Yeah, let me show this first. You get this rough phase diagram. So when R is large and positive, you can forget about B, and you're back to the old situation where you had the confining Neel order or the VBS order. But when R is negative, then B can condense and completely get rid of the gauge degrees of freedom. You can ask, what are these condensed phases? And now these phases have to break a symmetry precisely because of the non-trivial way the symmetries are realized by B. There is no trivial phase here. And what are the phases you get? Well, amazingly, you get the phases that you actually see in the cuprates. You see, first of all, you get a D-wave superconductor. That's a direct product of just the structure of the pi flux phase. It gives you a D-wave superconductor, which is seen. And you also get these stripe phases. This one is not seen, some circulating currents, but which one of these picked is dependent on the coupling constants at quartic order. So now you can ask, for some low energy theory, perhaps in between all of this, say near R equals 0, there is a conformal field theory. So what do you do? Well, the terms of the dispersion of the fermions and the bosons is exactly the same. So the fermions, of course, you have filled them, and these are the Dirac points. But for the bosons, you want to take the minima. And so there's two minima, B1 and B2. And you just take some continuum field theory near these points. And you can then express, so you've got now two complex scalars. You can express these broken symmetries in terms of the usual bilinears of B. So we put it all together, and this is in this paper with Main Christos, Henry Shackleton, and Zhu Lo. You can find a complicated phase diagram with this field theory. So the field theory that we talked about yesterday is just the first term. Then you add this. Now this is two-component fundamental SU2 fundamental boson B, and then there's a tuning parameter R and various nonlinear couplings. So again, now you have the Neel VBS order we have talked about. But nearby some D-wave superconductor, you can get a multi-critical point, which could be another true CFT with some field theory here. Okay. All right. So the purpose of this is simply to show you, this is mostly theoretical, but to show you that the pi flux phase has some very nice features. It can confine to the Neel state. And if you allow for charge fluctuation, it confines to exactly what's seen, the D-wave superconductor. The two phases that are seen are very natural products of the confinement of this spin liquid. All right, so now I want to turn to finite doping. The moment you turn to finite charge density away from half filling, you're going to break Lorentz invariance, and so there's no possibility for CFT or anything like that. But there's the possibility of actually connecting to experiments. So let me spend the rest of my talk to talk about that. What time is it? Okay. All right, so changing gears a little bit, let me talk about what happens when you have metals. You know, how does fractionalization appear in a metal? So first of all, ordinary metal you can treat as nearly free gas of electrons with a Fermi surface between empty and occupied states. And here's the Fermi surface of the cuprates when you move far away from half filling. And this Fermi surface obeys a very, very important theorem, which is the Luttinger argument or theorem. The theorem is that turning up interactions from the free Fermi state leaves the area enclosed by the Fermi surface invariant. Now, it could be that turning up interaction breaks some symmetry. Well, fine, you break the symmetry in your effective fermion theory, and fermions with the same symmetry will have an area that's independent of the interactions, same symmetry and the same density. Okay, so Luttinger proved this in some kind of perturbative Green's function argument, which assumes, although that's not explicitly stated, adiabatic continuity to the free electron state. But this was put on much firmer terms by Masaki Yoshikawa, who again, used these anomaly topological type arguments, reaching the same conclusion. Again, assuming, however, that the low energy, in his case, the assumption was that the low energy excitations are just quasiparticles on the Fermi surface. So building on Oshikawa's work, we pointed out, well, there can be now a new type of metal, which in fact the Fermi surface does not equal the Luttinger value. And that can be simply very stated. There is some overall anomaly associated with translation and charge conservation. And that anomaly can be partially satisfied by the Fermi surface. It can be partially satisfied by some spin liquid of the type we've just been discussing. All right, so that's what we call FL star. So now let me just show you a few pictures of different possible states you can obtain when you start from an insulator and you dope it. So of course, an insulating antiferromagnet has no Fermi surface. It's an insulator. If you put in a lot of holes, density P of holes, then you can get what happens at large P in the cuprates. You get what's called a large Fermi surface, where the holes are just moving around. But here an important point is that these are holes with respect to a trivial state, which is the fully filled state. So the fully filled state has 2 electrons per site. And so the number of holes here is actually 1 plus P, if I'm going to apply the Luttinger argument. And so the area enclosed by this state, which is just a conventional Fermi liquid, is 1 plus P over 2. Okay, another thing you could do is you imagine that you put in a few holes and the antiferromagnetic order is still present. So then what you have to do is just compute the theory of all the holes in the presence of the antiferromagnetic order. That's relatively easy to do. And what you get is the following Fermi surface. Now, because of the antiferromagnetic order, the Brillouin zone is halved, and you get these 4 pockets, but they are not independent because this pocket is the same as that pocket because they are related by a reciprocal lattice vector of the reduced Brillouin zone. So there's only 2 pockets of spin-a-half objects, and so that gives you a factor of 4, 2 pockets and spin-a-half, and so the area of these pockets expressed as a fraction of the Brillouin zone being 1 is P over 4. Okay. So those are broken symmetry states. So how about a more exotic state where you don't have the conventional Luttinger theorem? So one state is the following. where the spins form singlets and form some spin liquid, some very crude picture of a spin liquid here. But you also have these mobile holes, or holons. They should be called holons because when that holon is moving, it's not carrying any spin. So these are spinless charge E particles in this spin liquid state. So that's only possible because there's a spin liquid around. And if these are fermion, they'll also form Fermi surfaces. So now you haven't broken any symmetry in this state. And so you have the full Brillouin zone. And if they form these 4 pockets, there are 4 of them. However, they are spinless, so the degeneracy is again just 4. And so you get area P over 4. And this is a non-Luttinger area. This is not this is an area that's doesn't obey the conventional Luttinger theorem. Okay. Now, so by our argument, this is only possible if there's fractionalization around. There has to be a spin liquid around. And one consequence of that, there have to be these spin-on excitations. All right. Now, what could happen, and this is what we argued, is that the spin-ons could get attracted to the holons. And then they could form a bound state, which are these green dimers. So the green dimer is like a resonant bound state of a spin and a holon, spin-on and a holon. And so it has charge E and spin a half. So it has the same quantum numbers of an electron, and it can move around. And it might seem, you've done something where, you first took your electron and split it into a spin-on and holon, and you put it back together. Why bother? Well, the reason you're bothering is that the density of these electrons, or these spin a half charge E objects, is P. It's not 1 plus P. And so they will form pockets. There's no broken symmetry. But what's the degeneracy now? Well, there's degeneracy of factor of 2 for spin and factor of 4 for 4 pockets. And so you're going to get area P over 8. So, and this would be true for any spin liquid anywhere. And therefore, so to summarize, there's the antiferromagnet area P over 4, this doped spin liquid with area P over 4, and this FL star state, which gives you P over 8. And these are all robust answers independent of which spin liquid you use and all the details of your calculations. These are just, very rigid things. All right, so finally to turn to real experiments. So now this kind of metallic state I'm discussing is what's relevant for the pseudogap. And so there's been a huge amount of study of the pseudogap in the last 25 years or 30 years. I just want to mention the latest experiment, which finally succeeded in seeing some convincing sign of a Fermi surface above TC in this region here. And they measured something called the Yamaji effect, which is how the magnetoresistance in the Z direction due to a tilted magnetic field. And there's very special angles at which the dispersion along the third direction vanishes. And so you get peaks. And from those peaks, the angle of those peaks and this distance here, you can read off the size of the Fermi surface. So I was very excited to see that they, this is quoting from the paper, approximately 1.3% of the Brillouin zone is the size they see from these oscillations. And that's exactly P over 8. We're very close to P over 8 and very far from a fluctuating antiferromagnet. So this is, this particular violation of the Luttinger rule and the precise value of P over 8, P is 0.1, sorry. It's really the very best evidence yet, I think, direct evidence for spin liquid physics being relevant for the cuprates. All right, how much time do I have? No, I haven't. Yeah. Finally, I want to. About 6 more minutes. 6, oh, great, perfect. So now I have to put these two things together. I've showed you, what our understanding of the spin liquid in the insulator, and I think the pi flux phase is the preferred spin liquid there, partly because it's very naturally connected to D-wave superconductor. And next, I've told you about how you dope a spin liquid just in terms of pictures. Now I have to put that all together in some coherent theory, where you can make specific predictions for the cuprates that descend from the spin liquid. Okay, that's a tall order, but one approach that we found very useful and powerful in the recent years is what we call the ancilla approach. So this is just a technical tool, and you can think of it as a technical tool that makes sure you get all the anomalies right just by following some very simple rules. If you try, there's a huge amount of work on fractionalizing doped spin liquids. A lot of that work doesn't get the anomalies right. Well, okay. But here's a simple route. So the rule simply is you can always add in or remove degrees of freedom by some kind of RG. You can integrate out or integrate in, as long as whatever you're integrating out or integrating in is a trivial state that has some. So for example, in fact, what I want to do is add in this trivial set of two layers of qubits, one for each side. This is supposed to be a square lattice here. So I have 3 layers, but I'm just adding to each point on the square lattice another pair of qubits that are in a trivial spin singlet state. And the ground state of this thing is just a trivial product and has a gap which is J perp. All right, so this is my Hilbert space now. In fact, it's decoupled from the physical electrons with some Hubbard model U. But now I do a canonical transformation, which I can work out, at least in the limit of large J perp, where I couple this. And in fact, I can choose the canonical transformation to make these electrons essentially free electrons. So at least at large J perp, there's an exact mapping between this physical system that I want to study and this system that is very naturally gives me the FL star phase. That's the reason we're doing it. So how do I get the FL star phase from it? Well, you can now imagine that under renormalization, this coupling, which is a Kondo coupling, can become large. And then the top 2 layers are a Kondo lattice, and they will form what's called a heavy Fermi liquid state that's seen in thousands of heavy fermion compounds. And so what is it that happens in the Kondo lattice? So in the Kondo lattice, you apply the usual Lerninger theorem, and you conclude that the area enclosed by the Fermi surface is just counts all the electrons, including the spins. So here, I'm talking in terms of holes. The density of electrons here is 1 plus p. It's 1 here. So the total density is 2 plus p. And so you should get a Fermi surface of size 2 plus p. However, everything is mod 2 because you can always remove a filled band. So that's size p, and you get the required FL star pockets. Now for the Kondo lattice, this is the Lerninger value. But for the single band Hubbard model, this is not the Lerninger value. So the anomaly arguments tell you that there must be a spin liquid around to take up the missing anomaly. And in this ancilla method, that's foolproof. It's there. It has to be there on the bottom layer. You can't just forget about the bottom layer. It's there. And here we're going to take a pi flux spin liquid in the remaining few minutes. So now you can, at mean field level, get the binding of holons and spin-ons in the top 2 layers. You can put in your pi flux spin liquid, and I got FL star. And now this boson B that I introduced earlier is nothing but the hybridization between the bottom 2 layers. And you get exactly the same effective theory for B. So that's the basic theory. You have a Kondo lattice coupled to a spin liquid with this boson B. At the half filling limit already described, this Kondo lattice, that P equals 0, this is an insulator, forget about it. Then I just had B coupled to the pi flux spin liquid. All right, so that's what you have to do. And now we've done a lot of things with this. And I'll just run through various, of course, the reason for doing all this, we were doing this for a while, but the best experimental evidence this is correct is really this Yamaji effect that I just mentioned. But let me mention many other things that fall into place from this approach. First of all, there's the question of where, I've said they have to be the spin-on. There's a spin liquid here, down here. So why don't you see it? Well, in fact, you do. Okay, it just hadn't been appreciated. So here's the J1, J2 model that I mentioned earlier by Federico Becca. They computed in some exact diagonalization method, the dynamic spin structure factor. So if you have J2 equals 0, you have the Neel state, and you get this sharp spin wave excitations. But as you crank up J2, the near-CFT with this Z2 spin liquid that appears a bit later is right here around 0.4. And now you see that these very sharp lines have become big continua. And so this is one computation of the dynamic spin structure factor of the pi flux phase in this model. Okay. Now I want to compare this to RIXS spectrum, which not able to look at the interval zone. But all I want to mention here is you see very strikingly at 0 doping, you see the spin waves of the Neel state. And then you see these continua, which look quite similar to Federico's calculations, which I believe are the spin-ons of the pi flux phase. We're doing more calculations. There'll be more experiments to really check this out in quantitative detail, we hope, in the future. Okay, then how about the thermal transition to superconductivity? So here what we do is we just we take a very simple theory to begin with. We just forget about the fermions because the Higgs transition, the onset of superconductivity is associated with the Higgs transition. So we just take the thermal theory that I mentioned earlier for the boson B and an SU2 gauge field. So we just take this thermal partition function here, and so there's Monte Carlo results for this about to come. I just show this very striking snapshot here. So as you lower the temperature, you see this is the phase of the superconducting autoparameter in the x direction, and the y direction is exactly the negative one. And you see all these vortices and anti-vortices here, 2 pi vortices in the physical autoparameter. So the physical gauge invariant autoparameter is charged 2. But at every vortex and anti-vortex in this snapshot, you see these checkerboard patterns. And this is the charge order that appears for some particular choice of this H4. And that's supposed to be quite similar to the charge order you see in STM experiments in the cuprates. This is the superfluid density. Okay. You can also couple this to fermions in some Born-Oppenheimer approximation, where you think of static bosons but dynamical fermions. And then you have these are the actual mean field computation of the spectral density for photoemission, which looks just like an arc. But once you put in the thermal fluctuations of the bosons, you see that the arc, the pocket turns into this arc, which is much more closer to the experiment.
Subir, are we close to finishing up?
Yes. Okay. All right, let me just say this. Yeah, this is all. Okay, this is the last point. All right. So now, what about going into the D-wave superconductor? Does it give you the right type of quasiparticles? Well, so the D-wave superconductor, which is doped, has these pockets, and it has these 4 nodal points that come from the spin liquid. So the natural thought would be when you go into superconductor, you pair the fermions. Well, if you pair the fermions, you will get 8 nodal points, these red dots here, plus the pi flux will also be present. So if you apply a BCS mechanism to the FL star state, you get total nonsense. It's never been observed. However, if you apply a confinement transition to the spin liquid, then when B condenses, it can start mixing these two, and in fact they annihilate each other. And the actual nodal point you see is not the spin-on. It's this other particle. So this is something very special to finite doping. It's really this 4 points exactly that are seen. And this is exactly like a BCS superconductor. So the main message here is that the onset of superconductivity is confinement. It's not a BCS onset, but the final superconductor is smoothly connected to BCS state. All right, I'll skip the quantum oscillation, but also there's some problems that are resolved. So I just conclude by saying there's now pretty good evidence that the FL star state looks something like this, with a spin liquid with electron-like objects floating around above it. And then starting from that and confining the pi flux spin liquid in different ways, you can build the rest of the phase diagram. Thank you.
Yes.
So in words, what would you say is the mechanism that drives superconductivity here? No phonons?
Okay, so broad, yeah, great question. So everybody says, oh, there's a controversy about mechanism. There is no controversy. Everyone agrees antiferromagnetism is responsible for superconductivity. All reasonable people in the field, I'm sure you'll find out this. There has never been any controversy. So now the question is, how do we think about the onset of superconductivity, and why is TC so high here? Right, so those are questions we are trying to address. So you could start from the Fermi liquid here, and then put in antiferromagnetic spin fluctuations. So in the old style of BCS, you start, it's just a very BCS calculation, except the antiferromagnetic spin fluctuations are replacing the phonons. So that was actually already done by Scalapino in particular before the discovery of high TC. And they found D-wave superconductivity. All right, but from that, it's hard to see why, why should TC be so high? The other proposal by Phil Anderson in the early days was that there's some spin liquid present in the insulator, and then the spin liquid has the feature, as you've seen in these pictures, that the electrons already paired. Okay, so you don't need anything to pair them. The pairing is an intrinsic feature of a spin liquid. So why is it? So I think that proposal is correct. So why is it taking 30 years to make progress on it? Well, the spin liquid he was thinking about was some gap short-range spin liquid. I think the relevant spin liquid is what we are understanding now. It's this near conformal field theory described by this. And so now that we understand it well, we can certainly do all these things. And they work beautifully. That's my main message. So the point here is that when I'm coming down here, from here to here, okay, the spin liquid is just another way of talking about antiferromagnetism. Antiferromagnetism driving it, but the actual onset of pairing is something, yeah, so this is the words here. There's already pre-existing pairing in the spin liquid. So, but a spin liquid also has fractionalization and a lot of exotic features. So my bottom line is what you have to do is just take a spin liquid and you go to confine the fractionalization. It's a confinement transition or Higgs transition here in practice. And that gives you, all right. So it's also a fact that the highest, these are still the best high TC materials. And this kind of spin liquid-like region is only present in the highest TC materials. So phenomenologically, it seems like the spin liquid nature is very important because that's when you get the strongest coupling between the pairing and the antiferromagnetism. So can we use this picture to actually compute TC? Well, all right. I'm trying to get there.
All right, so now we'll take a short coffee break and we'll meet back at 11.